Okay, we'll talk a little bit about classic approaches right now. Being that this is a very old problem, there's many different methods and algorithms that people have utilized throughout the years to try and make some ground in this area, because this is a tough problem. As I mentioned, a lot of the early methods use very abstract notions of scene understanding based on pose, position, shading, and other quantitative and mostly qualitative factors, and for the most part, they did very badly. But one of the biggest names in computer vision and AI in general was neuroscientist and artificial intelligence researcher David Marr. Patrick Winston of MIT refers to his papers and philosophy in the field as the Gospel of Marr instead of the Gospel of Mark. So it gives you a bit of an idea of, what kind of a figure he was in early computer vision, and his ideas alone sparked, quite the resurgence in computer vision research. And he pioneered a bottom-up approach to computer vision, which used what was called a primal sketch, and this involved things like edges and light shading and things of that nature. And then from that, we would pull a 2.5D sketch, which added some features, added some nuances. I won't go into the complete details. I encourage you to do so. I believe he has 2 papers on the 3-part method, which is primal sketch 2.5D into a 3D model. And yeah, David Marr, brilliant guy. And I do see the potential for his style of algorithm and methodology to have the ability to come back, just because we've seen such a drastic increase in compute, and a lot of the problem with 3D scene understanding, as I'm sure you can probably guess, is extremely feature rich. There's a lot to possibly know at an objective level, right? Right. So following the rather mixed results of Marr's methods, the field shifted to much lower level and simpler problems like edge detection and image segmentation, which included things like thresholding. And this was just because we could not solve the bigger problems of things like mimicking the human visual system or a visual system more generally. These were far beyond our grasp at the time, and for the most part they still are. The 90s and beyond saw tons of uptick in both types of problems and the amount of them being studied. I mentioned that a little bit earlier with the application in more and more fringe problems, but things like image and scene classification, simpler scene classification, less sentiment and genre-based, and more just classifying what's happening. Pose length estimation and things of that nature just saw a huge resurgence. And that's still continuing into this day, with things like AlexNet in 2011-2012 that implemented dropout, that led to a new top 5 accuracy that just blew away the competition in the ImageNet competition. And it's only continuing on with things like capsule networks by Hinton et al., which are sort of recursive convolutional kernels that use the concept of consensus between these capsules in order to tell whether or not an image is part of one class or another. And these have reached a new state of the art in image classification, and I'll dive into those quite a bit more next lesson. Is optimal accuracy more important? Is the time it takes to prediction very important? Is training time important? These are all things you have to weigh when figuring out the best algorithm for the job. All right. So quickly going over these. SIFT and SIRP is a faster version of SIFT. SIFT, or Scale Invariant Feature Transformation, or Transform, is an algorithm that essentially just tries to standardize images according to their scale. So you can think that an edge or a curve or what have you would look very different depending on scale, right? So at 1 times zoom, it's going to look a certain way. At 5 times zoom, you and I will know that that is the same object, but it will look quite a bit different. And that's something that has to be, if not taken into account explicitly, it has to be, learned implicitly. But what SIFT tries to do is standardize against all those different scales. So it tries to learn features in a standardized scaling, and then it can account for this and learn image features independent of scale and independent of not orientation, but size in the image and prominence in the image. Okay, a Haar wavelet and radon transform, these are 2 different algorithms, and they're both really niche. I've only utilized them in the context of image similarity, which is trying to determine how similar 2 images are. And this is something, at least from what I know, I haven't read anything on it. Maybe, in the last 3 to 6 months, there's been some progress on this, but determining how similar 2 images are. And what these 2 algorithms do will create a signal or a frequency from the image, and you can then use that while it's, for the most part, naive. You can find the differences between, images that are, very different, or, say these 2 images are very similar. In between, these sorts of methods aren't very good. If the composition of the images are quite different, it usually fails spectacularly. There are very niche and fringe applications in which these can be utilized to great effect. A less fringe and niche algorithm, but still extremely useful, is Eduonix, and this was created in 2001. It's actually not an algorithm per se, it's a framework that incorporates multiple algorithms in stepwise fashion. And I'm not going to go into the technical details too much, but the main benefits of Eduonix is it learns simple square features, and it has very high ground truth predictions, and very low false positive rates. Additionally, it's quite fast, much faster than a convolutional neural network would detect faces or detect any sort of object in an image. So companies like Apple have and still do use Eduonix for facial recognition. They were the first ones to use it, I believe, with the iPhone in 2007, 2008. I don't know when they actually came out with the facial recognition, but they do use Eduonix still to this day. So it just shows you how powerful it is, and how effective it is, because very rarely do you see your iPhone detecting faces that aren't there, or not detecting faces. Of course, there's some fringe cases where you have your hair covering your face, or you're wearing a mask, or what have you. For the most part, this is a very solid algorithm and very effective in the real world. That isn't too testy, and you don't have to do too much optimization. For the most part, you can train it and plug and play, which is, the biggest upside of the algorithm. So, a bag of words model, these are utilized mostly in NLP, where you have a bag of words. Pretty obvious. But here, instead, we're going to use a bag of image features. So, and we try to classify an image, right? And we'd use something like naive Bayes, which is a probabilistic classifier, can incorporate those bag of words image features into the probabilistic classifier in order to make a prediction. Lewis-Kenide is a computer vision algorithm used exclusively in tracking an optical flow. And what optical flow is high level just tracking the path or the motion of any object through space relative to an observer. It's quite simple, and this is, I would say it's fallen off quite a bit. But again, like Viola Jones and a lot of these classic computer vision algorithms, their benefit comes in their speed, in training and prediction, right? As well as low number of features learned, and also low complexity. And adaptive thresholding is the last set of algorithms I'll talk about. Thresholding is a pretty simple problem in which we're just trying to segment an image by converting pixels to grayscale. So we will convert the nth pixel to grayscale based on the intensity of the color in that pixel. And as you can probably guess, this does lead to fairly good thresholding or segmentation, because a lot of the times in an image, high contrast will denote a edge, or will denote a border, or will denote some separation or segmentation of an image, right? So this is just taking advantage of that, and adaptive thresholding is just another layer on top of that, which we can optimize certain parameters. What colors do we want to be included in the thresholding? Do we want variation in intensities based on some factors like nearby pixels, or the gradient? So by gradient in that case, I mean a color gradient in which you have bright to a dark, or a strong color to a weak color, things of that nature.